So today I'm just going to basically discuss a few results from my dissertation and some conjectures. To give a title, basically I want to link two notions, which are on the one hand integrable systems, and on the second hand ratio of differential operators. So, integrable systems have many features, and they seem to be encoded mysteriously by a ratio of differential operators. And so, my goal is simply to understand the structure which lie behind them. But first of all, for those who... first of all, if you have any questions during this talk, please interrupt me. But what is even integrability? In the finite dimensional case, so if you look at ODEs, that is a pretty clear notion. At least there's something called complete integrability. So say if you have symplectic manifold M with the symplectic form W, 2n dimensional. Of course, you can consider the induced Poisson bracket, and then the evolution equation d over dt is bracket of some h, which usually called Hamiltonian, with u, is completely integrable. If one can find n functions, f1, fn, smooth function of n, which are in evolution for the bracket. Okay, which means that basically there are constant of motions for this evolution of the equation. And then there's a famous theorem, which I think is from Liouville and Arnold, which roughly states two things. First of all, the M can be foliated by n-dimensional submanifolds, and the leaves are preserved by the flow. And second, you can solve exactly the equation using what is called quadratures, which means finitely many algebraic operations and integration of non-functions. And maybe that explains why these systems are called integrable.
Yeah. Can I ask, how wide is the class of ODEs that can be written in this form?
Probably it's very small. But
so there is no general procedure to take any ODE and write it. So okay.
It really depends. It's so-called Hamiltonian ODEs. Yeah. It's not something you can do for general equation. Yeah.
But is there any way to recognize if given ODE can be written?
Yeah, I guess from this property here.
Okay.
Or maybe there's a smarter way, I'm not sure. Anyway, so that's the finite dimensional picture. And then now if you look at PDEs instead, the problem is there's no definition here. Okay, so if you ask me what is integrable system of PDEs, there's not good definition, but there's a couple of features. And the so-called integrable system possesses most of these features, which are the following. First of all, you can have infinitely many concept densities. I will define those things later, but first let me say them. Then there could be infinitely many symmetries in some sense. Not classical symmetries, but for those who know, there's also Lax pair formulation. So let's say existence of Lax pair. What does it mean? It means your PDE basically is compatibility condition of two inner systems.
It looked like a lax pair when it was over there.
You see too far away.
I knew they'd be
So this actually you can also see it in this classification. So the exact solvability.
Oh, that's ODE.
Again, in some sense. And maybe what can you say more? Maybe the existence of solutions. for instance, you might know that KdV equation has such. But as I said before, there's no definition. Why? Because the connection between those features are not clear. I mean, they're not well understood. Not to say that there are no connections, but there's no formal proof that this one is implies this one or anything like this. And so the theory of integrable system, some people say that it's more actually an art than theory, because it's a collection of recipes and meta theorems. There's no theorems. Today I want to kind of say that that's not true, but we'll see. So my goal is to, as I said in the beginning, to say that behind those features there's a pair of differential operators which kind of encodes everything. Yeah. But before I discuss this problem, maybe I should take 5 minutes to lay some definitions to explain what I mean by symmetries, concept densities. So. I don't want to spend too much time on definitions, but I have to do it. So what do I mean, first of all, by which class of equation I'm considering? I'm considering 1 plus 1 dimensional evolution PDEs. So it's something like this. Ut is a function of x, u prime, up to some point, u. And this means spatial derivatives. Now, it's 1 plus 1 dimensional, means that u is function of t, time parameter, and x, one-dimensional spatial parameter. So, yeah, and to make today I assume that this is a scalar, so say in R, but you can translate everything I say for vectors. It doesn't matter. It's just for sake of clarity. You can put R in here. Yeah, and what about the right-hand side? I assume that f belongs to some differential algebra V, which basically is an extension of differential polynomials in U. Okay. In which way I'm going to define like algebraically what I mean by this extension. First of all, here you have partial derivatives which commute. I assume that I can extend them here. So there are some derivations here which extend the partial derivatives and which commute. So commute this space. And second, of course, for every the element of V by abuse of language, I call them functions. So for every function in V, only finitely many partial derivatives are non-zeros.
So, do you include x into this algebra?
You can, but
so it's not.
They usually don't.
Yeah.
It's written in the first line. So.
Yeah, you can use it. I mean, you can put it here. Fine. And so, yeah, by the way, what is the total derivative here in terms of partial derivative? Can you tell me?
No, it's sum of these derivatives.
No, it's sum.
Weights, like
Yeah.
chain rule.
It's this way. Sum of u n plus 1 times this.
Yeah.
And so, since you have extended
Constant coefficients.
this here, you can just declare that this is total derivative in V.
Yeah.
So, it's total derivative in V. Yeah.
Just from a level. What if I want to include x? I mean.
Okay, then you just add
So.
d over dx here.
Derivatives
So.
of coefficients.
Okay.
First. Yeah.
And it all should be extended. Okay.
Yeah. Totally.
But you're right, it's the chain rule as you say. So, okay, the first step for me is that when I have evolution equation, I see it as a derivation of spatial functions, I mean, for V, just in the standard way, so. Yeah, so if I have equation ut equals f, you can consider the evolutionary vector field xf. which commutes with total derivative. And well, first of all, this determines completely this vector field, and the formula is similar to this one. It's the sum of f and d plus d.
Excuse me, there's some chalk over there?
Maybe you're right.
I think.
No, those are color chalks.
There's no
Yeah,
chalk.
well,
They're all color
Maybe
chalks.
you have one.
Big white chalk.
All color chalk.
Oh dear. Is that long? Tracking down to his fingernails.
Okay, we might have some here.
I got
Oh yeah? Wonderful.
Okay. So, by the way, this space of vector field is closed under commutator. So it's like in the finite dimensional case, if I take two of them and use them commute, what do I get? I get also a vector field, but associated to the Lie brackets of x minus x. Okay. And since this map here is injective, you can declare that this expression except g minus xgf is a bracket of f and g. Okay, and so that gives you Lie algebra structure on V. So on V you have a Lie algebra structure given by this formula and the total derivative. Now I want to define what I mean by symmetries of equation and concept densities of equation in this language. So first definition, G is the symmetry of ut equals f. This means that the transformation u gives u plus epsilon g preserves the equation ut equals f mod epsilon square at the first order. So if you want this infinitesimal generator of symmetry. But what does it mean concretely? So if I change u by u plus epsilon g, I get ut plus epsilon gt, which is the vector field except applied to g. Should be equal modulo epsilon squared to f of x u plus epsilon g u prime plus epsilon g prime, etc. And here, if you use the chain rule, this is just f plus epsilon. So what do you get? df du g plus df du prime plus etc. And you recognize that this is just xg applied to f. Okay, so basically g is a symmetry of f means that xf of g should be equal to xg of f. So it means that there are an evolution for the Lie bracket. Okay. And so, oh, by the way, I forgot to say something that in the features I exposed in the first place, all the so-called integrable systems have this infinitely many family of symmetries. So for today, at least, when I say integrable system, I just mean infinite dimensional abelian subalgebra V.
And is there any theorem that says that if there is such subalgebra, then we do something good? Like
With the
solve?
equation?
Yes.
Yeah, I mean, so when you have a Lie sphere, it gives you hope to solve this equation. I think in the audience there may be people who know more about how to solve these equations, but there's a theorem which relates this abelian subalgebras to pairs of differential operators, and once you get pairs of differential operators, you can hope to solve.
Pairs of commuting operators, or?
Oh no, they're not commuting operators.
Pairs of. Okay, I see.
Yeah, just think of like pairs if you know it.
Okay.
Okay, now just to finish definition, I want to say what is a conserved density, and move on. Okay, so if I take rho and v, say that it's conserved.
Could you please break the chart? Like break into pieces. Thank you.
By f, if so when I apply the vector field accept to rho, I get a total derivative, right? Which means that basically it's the integral of rho is conserved, is constant, and that by integration by part, this is the same as to say that f times the rational derivative of rho is a total derivative, where this denotes the sum of minus d to dn applied to partial derivative. Okay, just yeah. And usually the variational derivative of conserved densities is called cosymmetry. Okay, so now I think it's enough definition. So let me go back to my story. So I want to study this abelian subalgebras and somehow connect them to differential operators. So the starting point is a theorem from the 80s, I think. There are two parts in this theorem. Yeah, so I think the first one is by Ibrahimov and Chabad, and the second one Sokolov. So okay, let me take a function f in V, and then either you assume that f lies in an integrable system, or, which is not exclusive, you assume that f has infinitely many so-called cosymmetries. Okay, so
You mean like algebraically independent cosymmetries for it?
yeah, actually, you know, when you have a function in f, you can define differential order, which is the highest, the maximum integer such that u to the n appears in your function. And so you actually ask that this differential order goes to infinity. Okay. So it's more than linearly independent. You want that?
But if I have a conserved quantity, if I square it, okay, yeah, sure, okay.
So
yeah, sure.
that's here. I'm not talking about conserved density. I'm talking about their rational derivatives.
Okay.
Yeah.
And
But if you want to be technically complete, you should say that you should ask the differential order to infinity. Okay, and now what do you get from this? Maybe I can put. Then you get so the differential operator, which is the round series in V, coefficients in V, which satisfies some equation. So I think the right way to say that the Lie derivative along f vanishes. But what is this this thing? It is a difference of xf, the vector field applied to f, minus commutator with the first derivative. Okay, so you want this to be equal to 0. Maybe I can call it star. Okay, so that's the theorem. And now maybe a couple of remarks. First of all, it could look trivial, but it's enough to classify many such things. So let's say classification results. So if you restrict yourself to some algebras, let's say differential polynomials of some differential order, you plug it here, and this condition gives you a short list of equations, and then you check that one by one they're integral. So, but it's only for some subclasses of equation.
Are there any actual equations that appear in practice? Do they fall into any of these classes?
Give me one then, maybe.
I'm asking you, so
Yeah.
what's the motivation for this work?
Yeah. So, no, what's your question again?
Could you explain the motivation behind this work?
So, no, I'm just trying to link this class of equations called integrable systems to differential operators, right?
Well, so you're saying that you, well, the theorem tells you that some of the equations have some good property, right?
Yep.
Are there any equations that appear in practice that have those good properties? And if yes, then could you name some?
Yeah, sorry. So, I mean, the easiest one that everyone always quotes is called KdV equation, which is the following: ut equals u triple prime plus u prime. And if you don't, do you know it or not? If you don't, then it describes the motion of shallow water. But this is really like the canonical examples from like a lot of years ago. But there are really many others. Maybe I could quote Kucherov-Novikov equation, which is the following: u equals to u double prime minus 2 halves of u prime squared. And this equation has more relations to KP equation, which appears in representation theory. The list is very broad, so I could go on.
So there are some examples, and
Yeah.
what exactly would this say about such equations and how this helps?
No, so this precise theorem which would give you a way to classify first one, to kind of find them using this as a test. Okay. And the other thing is that then the solution of this equation, this L, would construct many actually symmetries that say good attributes of this equation. You would get them for free.
So you're claiming that this will help solve these equations.
So solve it would be the second step. I think first step it would give you the two things I defined. It would give you conserved densities and symmetries of the equation. And solve, I think you need to use, through this L, find a like pair for the equation, and then solve it. I think, yeah.
Okay. And in terms of implementing this,
Yeah.
are there computer programs that?
Oh yeah, this is. But you can only do computer programs if you specify yourself, you restrict yourself to some class of equation. For instance, if you do differential polynomials, then of course it's differential polynomials mean polynomials in U prime, etc. Like here. If you do that, then for sure you can. Yeah. Anyway, let me go on, and then maybe you have other questions later. Yeah. So it's a good test of integrability, but it's not a proof. By which I mean, I cannot go back from. So if L satisfies this equation, then okay, there's still a way to construct conserved densities, which is the following. So take the residues of its fractional pairs. If n denotes the degree of n are conserved.
Degree of L with respect to delta or?
Yeah, with respect to d, so to the total derivative. For instance, yeah. Why is that? It's because So if you just take k equals to n, then look at this equation. Let's say this is based on the lemma that the residue of a commutator is always total derivative. But this operator should also generate the symmetries of the equation in some sense. If
do you understand correct that these residues, their differential order doesn't grow?
no, they could, but you cannot prove it like this.
Okay.
So that's what I mean, that it's not completely satisfying, because if you just take a solution like this, you build this function and you cannot really prove that they go to. You could, but you need more information.
So on case by case basis.
Yeah. If L is a differential operator, then it makes sense to apply it several times to F, and in this case, you get symmetries. Okay. But of course, the problem is, most of the case it's not differential operators, it's actually series. So what is
n?
Sorry?
N
N is integer. What is L applied to F for L pseudo differential operator? Okay. For instance, what is the inverse of U in differential equations? Okay. Now,
Yeah.
fortunately, in all examples, it's not any series, but it's the ratio of two differential operators. Let me state it as a conjecture, which means that you cannot prove it, but it's always true. Okay. So for any integrable systems, which means infinite set of commuting flows or symmetries, you can find A and B differential operators such that the ratio satisfies sum. By the way, as terminology, since this is supposed to generate symmetries, it is called the recursion operator.
Quick question about the beginning, which I missed it.
I noticed.
So you're saying some, F is an integrable system. So you defined it in some way, some abstract way.
I didn't actually define it. I said at the first place that there's no good definition because the integrable systems it's a class of equations, okay, which have several features and are not well connected to each other yet. And as for today, I took the definition that when I say integrable system, I mean there's infinite family of commuting flows, okay, or they're also called symmetries. And in the end of the day, I want to say that they're connected, but if you ask anyone who knows theory of integrable system, could never give you a definition. So it's something which exists, okay, believe me. And it's a class of equations which have many interesting properties.
So theorems proved?
No. Today I want to prove theorems. Don't worry about it. I will not. This is the only conjecture I have for you today. The rest is theorems. Yeah.
How do you?
Did they prove a theorem?
That's one theorem too. But I mean.
But there was a definition.
So this, you see, relates. It goes in one direction, but not both directions. So you cannot really unite.
Yeah.
Okay, but then so you're talking about some definition. Okay, so some infinite something.
Yeah.
How is it related to? Can you express it in terms of solving the equation?
I understand you're interested in solving the equation, but maybe it's not focus of my talk today. So, I mean, yeah, you want to say something?
Oh, no, I was going to ask you.
It is in my understanding, this class of equations, the main method to solve it is based on Lax pairs.
It's based on what?
Lax pairs representation. Yeah,
Lax
pair
pairs.
representation.
Yeah.
So,
And so
Can I have a question though?
you can.
A naive question?
Yeah.
How do you apply the operator B inverse to a bona fide function?
Actually, you have always very good question. That was my next. Yeah. So.
Can I check I understood your last statement, which is if you assume the conjecture is true, that
Yeah.
every integrable system with the definition you've given then has an infinite number of cosymmetries. If you assume the conjecture is true.
No, that's so. The conjecture just says this, that I can find. So this is a theorem that I can find a series. The conjecture just says that in practice you can express the series as a ratio of two operators. Okay.
But we're still
And
not
then-
necessarily in the class.
Exactly,
No,
yeah.
that's a differential.
Exactly. And then what do we mean for your question?
What good does it do you to
Yeah. So what do we mean by?
introduce the fraction field?
Yeah, first of all, it's a field because the ring of differential operators is Euclidean,
Yeah, I know. I mean, yes.
and it's a right and left Euclidean, so there's no
Yeah,
problem.
right. But applying it and
Yeah,
getting
so
some
yeah, you're right.
mileage out of it.
So what do I mean by a ratio AB inverse generates integral systems?
Yeah.
It's pretty easy. So first of all, you start from somewhere, let's say F0, and then you realize that it's an image of B. So it's B of something, which is 0. By the way, this is in B, but if you want to be complete, this should be in K, in the fraction field sometimes. And then you apply A, and you get a new function, F. And then you realize that it's still in the image of B. And then, of course, what do? You apply A. And then it goes on infinitely many times like this.
Oh, I see.
In the case where, for those who knows, in the case where they're both Hamiltonian operators, this is called Lennard scheme, but it's more general actually. We just call it scheme of integrability.
Yeah.
So in practice, this is the way all the symmetries which are here are constructed. And if you wish, it's the data of three things. First, those functions. Of course, that the chain condition that A of Gn is B of Gn plus 1. And then, of course, also you want them to commute. So B of Gn. Gn equals 0. So this is precisely what we mean when we say that this ratio generates an integral.
excuse me. What's that symbol? That looks like a K.
Oh, it's okay, actually.
It's okay.
So it means that those functions belong to some differential ring or algebra V.
Yeah.
Yeah.
But sometimes to get the arguments must lie in
So.
the fraction field.
Oh,
It's
K,
just,
K is the fraction.
Yeah.
You can forget it if you want, but that's to be precise. Yeah.
Okay.
That's good. Because V is the main.
Fraction field. Right.
So if I have A and B, can I somehow check whether such infinite sequence exists?
Yeah. So
That's why I asked.
where are the problems? Problems are this and this, right? So, and the basic question is, okay, so in practice you have integrable system and you can find these things. That's kind of magically, right?
Yeah.
So my question is the opposite. Is for which AB can you do it? Okay, for which pair AB can I construct an integrable system? So first, what I'm going to do, I'm going to find necessary conditions on AB, and then I hope that it will be sufficient. Or if it's not sufficient, at least it'll be close to the sufficient condition.
Why would you like to answer this question?
Because it's always good to understand better the structure which are behind things. I mean, first of all, for one thing, these systems are, I told you from the beginning, they have different features which are studied independently, but not connected. They should be connected, you know, because I don't believe that there's magic here. They should be connected. And a way to do so is to study the structure of these differential operators, which seem to be behind everything. I understand your point of view. This is not directly related to solving the equation.
So
But
the goal of this is to bring order into the definitions.
that could be one way to say, but it's not only bring order because if you have more rigor, you can prove more things basically, you know.
What do you mean more rigor? Is it just rigorous or not rigorous?
No, it is. This approach I think is rigorous, and so you can prove more things, which are
You
of
think that
interest.
other approaches are not rigorous.
I'm not claiming that directly, but maybe that's true. So, what did I want to say? Yeah, actually, to go on this, for some experts in the field, there's no question, okay, because they think that there's a class of operators which is sufficient. Namely, if you're in this class of operators, then you can construct diagnosis. So let me talk about this briefly. Maybe I don't have enough space. So they're called hereditary operators.
Can you give us an example of a pair
Yep.
that gives you an
Maybe-
integer system?
Maybe give me
Later, maybe?
3 minutes,
Yeah.
because
So that's a way of creating
So-
integral systems.
so definition. So what is hereditary operator? So N is hereditary. So in a very formal way, it
Two
means
looks
that
like an
the
exact
9-house
condition.
tensor is 0. But and 9-house tensor is something which, when you have almost complex structure, it's complex if and only if. I mean, it defines a complex structure
Oh, no,
if and only if
equalizer.
9-house tensor is 0. But here, let me be more concrete. This means that for all function f, what I defined before, like the derivative of L along AF, is L times the derivative of L along BF. That must solve for all f, okay? And the claim is that the claim of this paper is that if this is satisfied, then AB inverse generates integral system. Of course, here L is
Claim or theorem?
it's meta theorem. No, it's
So it's
you
a
can find
conjecture.
you can find this. No, you can find this as theorem in some papers. You can see it.
Yeah, but is it proved?
It's proved, but it's false. So. I mean, I'm just mentioning as curiosity, and then I give you contact. So, for instance, you can check if you wish, but if you take something that simple, the inverse U prime D. Of course, here I write always A the inverse, but since it's a field, you can always permit. Okay, this is hereditary, but does not generate integrals. Let's say it doesn't give. Okay.
And could you name a few authors who?
I don't want to name people like that because also because some of them I work with, and so. And once I went to see this person and I said, I proved this, and she said, hey, I also proved it. No, anyway, it's just to give so that you have this notion in mind. But now I can answer the question kind
Well,
of
of course,
directly.
the obvious one.
So theorem. Okay, for one thing, let's assume 1 and 2 first. So let's let L, Gn satisfying 1 and 2.
Oh,
And the question is, when can you say that? If this is true, when can you say that they commute? Okay, so 3 odds if and only if 2 things. First of all, L must be recursion, which is where I erase it, but for the first one, F0, which was this equation here. And second is something else, which so L is A inverse, condition that A plus lambda B for any complex number lambda is, so okay, here I call it integrable, but that's because I didn't find a better name. So it's it's a class of operators, differential operators, not rational, which I'm defining now. Definition. So, differential operator C is integrable if its image, so the image of C, which can, it doesn't have to be the whole thing, is a sub-Lie algebra. Sub-Lie algebra of V. So I mean that if you take any F, any G, you take the bracket CF with CG, then you must lie in the image of C. Okay? And that is the condition. So for them to come in.
Can I ask a bit about the initial question? So, might happen that L doesn't generate the integrable system, but if I enlarge my differential algebra joining some integrals, it will.
Yeah, so the point is to not try to do too much there. Right? It's like to try to stay local as much as possible.
Yeah, but the joining integrals is not that bad. I mean, people often do this.
No, but sometimes...
Or it doesn't help.
Integrals of what?
Of differential polynomials or whatever. Okay, integrals of elements of V.
I'm just saying that sometimes...
Yeah, but all of it's just some formalism. What's the meaning after you do this in terms of the equation?
Integrals of functions?
Are you sure? This is how this translates.
I hope. That's why you're asking.
Okay.
So sometimes it's not that easy to extend the thing.
But
because
might it make sense to extend?
It might in some conditions. Sometimes doesn't make sense. Because let's say if you extend, if you take differential polynomials and you say, okay, I want to take integral of U.
Mm-hmm.
Yeah, but then maybe when you take the flow of this, you cannot express it in terms of U prime, and you need to extend even more.
So you
it's
mean
not
that
sometimes.
I can take total duty?
So if you start from an equation and you want to extend your field, sometimes the equation is not closed under this extension. It's subtle. I'm not sure I want to.
Wait, let me just put the question other way.
Yeah.
Does there exist such L that it doesn't generate integrable system, but it does after enlarging V? So is your definition algebra dependent?
Yeah.
I don't think so.
So you think that it doesn't depend on
No, I don't think it depends.
Okay.
Yeah.
That was my question.
Yeah.
Thank you. But you don't have a proof of this fact.
No, also because another thing I don't have proof for counterexample is the following thing. So I'm saying that if I have this kind of operator, then it fully satisfied. I cannot prove directly that 2 is, but I don't have counterexample to it.
So by the way, so you give 2 examples of concrete equations.
Yeah.
Would you reserve a few minutes to show step by step how all of this applies there?
That what?
Could you illustrate your definitions and acts with those concrete examples, so all the objects explained?
Let me give you examples for this class of operators. Okay, and then maybe I will mention some equations. So if you want to be very concrete, let's start with polynomials. So you look for operators whose coefficients are in this ring. And maybe if you want classification, you always need to be more specific. So let's say you impose the degree of B to be 1 and degree of U to be 1. And then what do you get with this condition? Actually, you get a short list. So the first one is D. The second one is D times D plus U. And then I'm just going to go a little bit more too much. So if I draw edge, it means that the upper one divides on the left the next one. And that's the only one you get in degree 1, 2, 3. And then you get 2 in degree 4. 2 more in degree 5. And
do you draw the classification of integrable operators?
For some exotic condition. Just as an example. So that's 5, I guess. Because it looks strange, that's why I'm doing it. And then it repeats like this, and symmetrically. Like this. And these patterns go all the way. And again, I mean that this, when there's an edge, it means this guy divides on the left.
I don't
This guy.
understand.
Yeah, let me explain one more thing. So, this picture here, every point is a differential operator. For instance, the first one is D, second one is D plus U. And every line means that the degree is, so degree is 1, 2, 3, 4, 5, etc. And when there's an edge, it means that, for instance, this one divides on the left, this one.
It,
Divides on the left, for instance.
oh, okay. Yes.
This one, of course,
Yes,
is
yes,
here,
yes,
right?
yes, yes.
And that's the only thing you get. But and then once you have this operator, if you want to go back to integrable
This is the
systems,
degree.
you need to take ratio of two such things. So for instance, if I take the simplest thing I can imagine, take the ratio of this one with this one.
What the degree one?
The degree is the highest power of.
You the operator's polynomial. That's a degree.
Polynomial?
Well, the degree there is, well, you put a D inverse in there.
No, the degree is the highest
Degree
power
D
of
is
D.
1.
Oh, okay.
So
okay.
it's
one
You mean
highest
order.
power.
We will
Yeah.
call it order.
Yes,
Okay,
I should have
alright,
said that,
alright.
sorry.
So this operator actually generates integrable system, which
See,
probably
that's
you
a
know.
polynomial.
It is
That's a rational
yeah,
function.
okay.
it's the Burger's equation.
Hey,
Um,
I like that one. I
But-
didn't recognize it.
this this condition here, I said is exotic because of course you can have many other examples, such as so again, if you go back to KDV equation, which is UT equals A here is the double prime.
Oh,
which
I
is
see.
prime.
So there has to be some canceling some of those inverses.
You can
Otherwise,
consider
what's D inverse
UT
of
plus
F?
TUV.
Integral.
Burger's equation has degree. What is it? The heat equation.
Do you have more questions? Or? No.
I have a question.
Yeah.
So again, so you mentioned those two equations, KDV and I don't.
The Burger's equation?
No, something else. You
Oh yeah, Krejcir-Ronnovikov.
Really
Yeah.
pretty.
So how is the integrability shown? Is it some ad hoc proof or is it?
You mean exact solvability? How is the
So how do you test integrable system?
So, okay, do you want me to say how do you prove that there are infinitely many symmetries, or do you want to prove that you can solve it? What's your question?
So either way.
Okay, the first way to prove that there are infinitely many symmetries, I have just
Oh.
theorems to state it.
So is it that it's ad hoc concrete proof for each equation or not?
Yeah, I have concrete proofs for both.
So it's not that there is a systematic approach. That's,
No, so that's what I said from the beginning. I wanted first to find necessary conditions, and then they're not really sufficient, but I'm
Yeah.
extending them a little bit to have what you call systematic approach. It's not good enough to cover all the examples, but it covers most of them.
Mhm.
For instance, the two you quoted, that works.
But still, it's not. You don't have an algorithm to decide. So someone gives you an equation.
So if you're interested in, no, I think if someone gives you an equation and then I think you have to go back to the theorem that I stated first. That would be the best algorithm to test integrability.
So is it decidable or not?
Yeah, but with the theorem I gave you first.
So it is. The answer is yes.
Yeah,
For a given equation.
for a given equation, yeah. Yeah.
But not for given, but is there an algorithm that for all equations can test? For one
Then
equation,
I'm not so sure anymore right now, but
I'm not so sure.
I mean, of your second question, yeah. I mean,
For each given equation, of course, there is an algorithm.
Yeah,
There
yeah.
are two algorithms. One says yes, the other says no.
no. That's not that's not an algorithm.
Okay.
No, for even any given equation, you can use the test that I wrote in the first place, and that's efficient enough. Like usually, roughly speaking, if your equation is of order n, you need only to compute n terms in the series, which I defined first. And then if you are obstructed, it means it's not integrable. But that's not theorem, it's just experience. Yeah. Okay. Now what I did here is more like once you have your short list of equations, you can prove that it's integrable using my results. But it's not a way to. If you want to find new equation, what I would do is I would compute. This is very easy condition to check. So it's easy to find new examples of such things, and then you take. If when you look for such operators, you find a family depending on one parameter, then you probably have a new equation. But that's not what I was going to talk about.
And other equations for which the answer is unknown and one would like to find out.
Yeah, I mean, this is mostly true. So all I'm talking about today is differential equations. So like ut equals a PD. But also you can do the same with ut equals discrete. So for instance, if you take a lattice with, E0 is just Z. And for instance, you can consider U1 minus U minus 1. Everything you can imagine. For this kind of equations, which are called differential difference equation, it's not. There's a lot of unknown things, and so and all these theories basically apply to this case modulo. I said most of it, so you can use it in this case. Yeah. Actually, that's what I'm doing right now. But today I don't want to talk about. Yeah. So this class of operators just satisfies 3. Now I erased what was 1 and 2, but basically the question you're facing is why is it in the image of B, of the denominator? So let's say you're given L, which is, I called it integrable. And recursion for the first function. And now the basic question is why is at each step why is A of Gn in the image of B?
So by the way,
yeah.
In your examples, the coefficients don't depend on T, do they?
On T? No, but it doesn't matter. If there was some dependence on T, you could also deal with that.
And that's the same, goes the same way.
Yeah, I mean, not exactly the same way, but you can go somewhere. Yeah. I just decided not to talk about it to keep it more simple. Okay, and this kind of goes back to your question, because you would say I extend the field and yeah, but here I want to stay local. So from this point, I'm making extract assumptions which I think are not necessary, but I need them to prove things. So the first one is. Sorry.
Yeah, so I apologize. One more question. So you were mentioning that in your kind of intuitive procedure, so you have to check something up to some order.
Mm-hmm.
To go, and that order is usually related, or maybe equal to the order of the equation.
Mm-hmm. That's correct.
And does this would this change if you have T?
You see, I'm not sure. Don't want to say nonsense, so I don't know about this. I would bet no, but I really don't know. Yeah. Sorry.
Thank you.
First of all, this can be trivial in the case where B divides A. Right. If A is B times C, then there's no operation because image of A is contained in image of B. For instance, that's the case with Burger's equation, which is D plus U as the inverse. Okay, but for the rest, there's really no way. So I make this. You could say artificial assumptions, but which covers most examples, which is that the degree of B as differential operator is the dimension of its kernel. So if you want, the kernel is full. The kernel B is full. Okay, and in this case, first of all, you can write L is in a nice way. You can say L is some differential operator plus some something which is called weakly non-local. So this is called weakly non-local operators. And actually, it is equivalent. Okay, so you can write L this way if and only if B satisfies this.
Who are E, P, and Q? Where do they live?
Okay, so E is a differential operator, and Pi, Qi are in B.
What does weakly non-local mean?
So it means, local kind of means that you would only get the differential operator. Weakly non-local, it means that the part which is not differential operator is as nice as possible.
Excuse me.
That's the idea.
What is if and only if?
So
What's the other sign? What's the other sign?
L is equal to A B inverse, right? So I'm saying that A B inverse can be written like this if and only if B is like this. Yeah. Anyway, so and then how do you test that?
What does D mean there?
Sorry.
What does D mean there?
Oh, D is the degree of differential.
Oh, the degree. Okay.
Yeah.
For instance,
The dimension of the
the
kernel.
degree of this is 2. Okay.
So, like, if I adjoin all solutions of B, then this assumption will be satisfied.
Yeah, but you see, you cannot. For some technical reason, you cannot.
Why do you use the word assume?
You can. Yeah.
Assume it's the dimension. Well,
I mean, I still hope that I don't need
I
this.
mean, you
assumption.
say if and only
Where
if
is
you
the
don't use the
kernel?
word assume.
no, but if and only if goes to there.
Okay, so
L
goes to
equals it. Wait, no, I'm confused.
please ask a question.
Oh, I don't know.
Why do you write the word assume?
What is the statement there?
Sorry, I just yeah, okay.
Yeah, that's a good
This-
question.
Okay.
This is a proposition.
Right.
D
That's
then
fine.
I assume-
equals
I assume-
dimension.
I assume that it's true.
Yeah.
Oh, you assume it is true.
Yeah.
You assume the if and only if.
No. I don't assume the proposition is true. I believe it's true.
That's a good idea.
I mean, I prove it's true. So
Right.
this is a proposition, and
What's the
then
equivalence?
So what's the assumption?
here there's no assumption. It's proposition.
Oh, okay. All
So-
right, fine. That's fine then.
Yeah, and then now.
Because that throws me off. But
Sorry, and now I assume that one of these two equivalent statements. So I assume.
DB equals the dimension.
okay, all right. Fine.
Assuming-
Okay,
No,
all
wait
right.
a minute. What's the statement?
The statement is the two things are equivalent.
What
And
are
then-
the two
And then he
things?
assumed that holds now. Okay?
It refers to what? The first equality?
If any one of them holds,
This is equality. Yeah.
Yeah, it.
then
That
That's
is it.
true if and
It.
only if
That is it.
that's equal to
What do you
AB
mean, it?
inverse.
You have
it.
second word in second line.
Oh, sorry.
That is it.
it is the problem.
Yeah, it's either this one or this one. You pick
Yeah.
your favorite. So
I
this
mean,
is,
if it holds, it's called weakly non-local. is
yeah,
that
this
correct?
kind of operator is called weakly number.
Where does the kernel live?
So I'm sorry.
Where is the kernel?
Oh, okay.
Where does it live?
Okay. You know what? If you want me to be really rigorous, here you have to put k. Okay, and then k everywhere,
Okay.
which is the fraction field of.
Oh,
of B.
okay.
But
Fraction field of the operators?
anyway,
No.
let's don't be too technical. So A of Gn is in the image of B. This is the same as to say that Qi times Agn is total derivative.
So you have a field of functions.
Okay, for okay, now so in the end, what I'm trying to do now, I want to state a theorem which gives you sufficient condition. And I don't want to put too many assumptions in it, but unfortunately I might have to. So let's sum up. What do I know about L? L is integral, which I defined before. It is recursion for the first one, so for F0. And it is weakly non-normal. Okay, so you could say proposition. Now from these three assumptions, what can I say? I can say that the variational derivative of f times qi is okay, belongs to the space spanned by the extensions. That's one thing. And second, I can say that the Frechet derivative of qi is self-adjoint, which implies that qi is variational derivative. Now remember, what I want to say is that I want to prove AGN belongs to the image of B, which means that qi times this belongs to the total derivative. So here, I have two ways to conclude. The first one is you have to assume that B can be broken in two parts. Which is so it's if you want Z mod 2Z graded. And this switches parity, while variational derivative preserves it. For instance, if you consider differential equations and you let the parity of u to the k be the same of k, that works. Okay, so now let me state some theorem. So take L as above. And assume several things on top of it, that f and the pi's are odd, and that the qi's and E considered as differential operators are even. Then you can construct an integral system. Okay, so once more, this kind of artificial conditions, but two things, they fit most of the examples and they give you a very easy proof. I mean, for instance, here, this space is even, and this function is odd, but this operator preserves parity, so that this has to be 0. Yeah, I don't think I want to enter too much into details of this theorem, also because it's... yeah. And the second one that I can state without putting any parity on V is the following. Okay, so we know that the QI is a variational derivative. And now when I want to prove that f is in the image of B, I want to say that f times, sorry, you have to prove that f times this variational derivative is a total derivative, which means that ρ is conserved. And remember that L is a recursion for f, and in this case, you have for free conserved densities, which are the residues. So if you assume that, so theorem, other ones, if you assume that rho I belongs to this space, then you don't need any extra assumption. Then L generates integral system. Okay. Okay. And now maybe the last thing I want to say is to compare this class of operators with Hamiltonian operators. Okay. So I assume not everybody knows what it is, so I'm going to define it. It's just a generalization of Hamiltonian mechanics in fine dimensions to PDEs. So definitions. Maybe I can draw it as a comparison. So this is fine dimensional. This is infinite dimensional. So here I have a smooth function on some phase space. Here I have my V. And this is equipped with some Poisson bracket. And here it is a rational differential operator, which is skew adjoint and induces some Lie bracket on V mod A. Now, what is Hamiltonian equation here? It's something of the form d over dt is bracket of h with u, and here it is d over dt is h applied to some variational derivative. Yeah. Okay. Now, most so-called integrable systems can be written in Hamiltonian form for two compatible structures. So what is the relation with what I said before? Proposition. If H and K are compatible Hamiltonian, then the ratio is integrable. And conversely, if you wish, so if W is an integrable system, which is Hamiltonian for H, which is Hamiltonian for H, and generated in the sense I explained before by some rational operator L, then it is Hamiltonian for any operators of the form L to the k times h for k integer. So the moral of the story is that if you have one Hamiltonian structure, then you have infinitely many compatible, provided that your system is generated by this L. But it's always the case. So. Okay, so now I think I'm almost done, but if I want you to remember one thing, is basically that I talked about three classes of operators. So how do they compare to each other? First, the thing I introduced was called integrable operators. And to me, this is the right candidate to generate all the integrable systems. They are included in the class of hereditary operators, which is widely known, believed to be sufficient, but is not the case. I gave this counterexample here. And also, most integrable systems have bi-Hamiltonian structures, but not all of them. And so the class of, let's say, ratio of compatible Hamiltonian is strictly included here. For instance, if I take d plus u, the recursion of operator for Berger's equation, it is here, but not there.
So actually you want to write strict inclusions in both.
You're right. Yeah. So basically this is too big, it's big, but it's kind of too small. And so I think that's the right answer. But my two kind of sufficient conditions are a little kind of have too many assumptions for my test. I believe they're not necessary, but cannot prove it. So.
Do I understand correctly that your results apply to the middle class?
Yeah, that's right.
And somehow help you to sometimes check whether the operator, the equation is there.
Yeah, and actually there's a connection between this one and this one. Which means basically that most of the times when you multiply one Hamiltonian by integrable operator, you get a Hamiltonian operator. Yeah.
Oh, okay.
But you're right. All the results I stated were here, not there. So you can apply. You can say more things here, but it doesn't apply to our equation. So. Yeah. Anyway, I think I'm done. So if you have any questions, it's open.
Can you suggest some reading for someone like me, who's totally ignorant of this approach? But
Yeah,
very
so
interesting.
the guy who's
The beginning of.
who likes the more to write about it. It's called Vladimir Sokolov. So he's not the only one, but
Okay.
I think the name is called What is Integrability? It's a big review book. I know actually that right now he's writing another one, but which is not
I
published
think I
yet.
have that downloaded. I should read it.
And it has a part of this book which is by him and someone called Mikhailov.
This approach, does he?
I would say yeah.
With
I think it's called
inverting the
symmetry of
operators
proportion. Not exactly the same, but you would find
What about this approach? Your approach?
I mean, it's
His papers.
yeah. I guess.
Read. Oh no, that's at the highest level. I'm at the
Oh
bottom.
no, you mean so you ask for instance the first theorem I stated like this
Yeah.
here you
Yeah?
find
Oh,
you
okay.
find it. And then by the way in this book there's a second chapter where people use number theory to classify stuff.
Sokolov.
And there's also more analytical parts of the problem. So
Oh,
it's really complete.
okay.
Yeah.
Yeah. And do you use any cohomology with on the conditions of
Yeah, so
the image of B
cohomology usually appears more when you deal with
in the Hamiltonian
yeah.
part?
So
Okay.
for instance,
So, but not in this part so much.
yeah, I mean maybe there's where you didn't think
Yeah.
about it.
That's later. Yeah.
Somehow so I was working with Victor Castro and he likes to think of this as through the language of vertex algebras somehow.
Oh.
And of course when you do this you have many
This
cohomology byproducts, but I did it kind of more I don't know, different at least.
It's amazing that you can make such good use of inverting the operators in terms of this whole structure and then creating
Oh, by the way,
systems.
By the way, this scheme which you talk about is widely known as, because it was discovered for compatible Hamiltonians, and it's called Lennard's scheme.
Mikhailov. Yeah.
And by the way, the condition that I said here, so I saw that it was necessary condition, but people randomly studied them before without knowing what it is. And that's why for instance, the list I gave you here with the tree kind of, it was like a curiosity that some people, they wrote like a short paper on that.
Yeah.
But they didn't know what they were doing.
Yeah.
I ask about this Ibragimov-Chabat theorem? So, how can I understand? So, it states that there is this pseudo-differential operator,
Yes.
and then you say that it's in many cases it's rational.
Yeah.
How can one check that it actually is? I mean,
Okay,
is
first
there
of all, yeah. First of all, if you take this equation we're talking about, once you have one solution, you know the set of all solutions, and they're like this. They're just, how do you write it? Maybe Laurent series in L, with coefficient in C, like this. Once you know L, this is the set of all solutions. So it doesn't help you much to see if it's rational or not. Usually you just, okay, if your general question is this, you give me a series and you ask me, is it rational?
No, I give you initial OD.
Yeah,
then you...
Yeah, but then I would get a series,
Yeah.
and then I would face the question, is it rational? So there is a way, let me write it. Okay, there's I guess two ways. First, if you assume that on top it's not only rational but it's weakly non-local, then you can try to find who are the PIs and QIs. Otherwise, if you write as unknown A, unknown B, it gives you two equations, because it gives you... So you want to solve this. And basic theory of differential operators tells you that this is equivalent to two equations. Okay, you assume that they are coprime, right? Gives you this xfa is I think ADF minus this or something similar, and then xfb is the same age.
What is H?
It's another unknown.
No.
So you have
three
A, H, and B.
So, and I have to try this for all possible orders of A and B? Or...
You know, if you want to implement that, you have to make some assumptions on order of A. No, you know the order of H, of course, because it is the same actually as the order of DF.
Okay, but...
So, at least that's fixed, but then for A and B, you need to make assumptions.
So then there is no a priori understanding how large...
No, there is. You can say something about the difference of degree of A, degree of B. It should be related to the order of the equation.
Yeah, sure,
but for A itself and B itself, it's up to you. Yeah.
So you don't. So a non-algorithm is not known.
No, it's something with a mix of hands-on work and algorithm. You have to make a priori ansatz on A and on the sides.
There's
No.
So do you agree that questions about PDEs are often supplied with initial and boundary conditions?
Inverse. Yeah, I know this.
So how is it? Does it relate to your work at all?
So again, I'm mainly algebraist, not too much analytics person. I know that for again. So if it's, by the way, if it's not true, then you can contribute. I think to find for solutions of this equation, you need lax pair, and then actually the initial condition is crucial, which means that for some initial condition you cannot actually prove that there's some very easy equations in this class for which you cannot prove the initial value problem. For instance, for KdV equation, actually I'm not sure. I think if you assume that initially decays at infinity, then you can solve it. But if it's periodic, maybe not even. I'm not sure.
I was going to say Burgers would be the easier counterexample.
What is counterexample?
So if you want a smooth solution to Burgers,
Yeah.
you can take something that forms a shock in finite time. It's not smooth.
Okay. Yeah, so it really depends on the initial conditions. My ears were better. It's not your ears, it's my accent.
Thank you.
Yeah.
Is it possible to have AB inverse equal to CD inverse?
Oh, and then what happens? What do you think?
I mean, can an L be represented as a quotient
So
in
I didn't.
two different ways?
Of course it can, but I didn't mention all my theorems, I have to assume that A and B are co-prime. Because, yeah, A and B are always co-prime, so there's no common factor on the right.
Oh.
Otherwise, yeah, of course you could do that.
Oh, I see.
Yeah.
So, I mean, it's real fraction, you're saying.
Yeah.
Then,
PM cone.
then when you say, when you ask the question about the bounds on the degree,
Yeah.
you're talking about the lowest.
Oh yeah, the lowest possible, yeah. Yeah, and as I said before, now I'm considering examples in differential difference equation. It's the same, but what's the main difference is, so between this and let's say this, where, okay, this is derivation, this is automorphism. What can you do here, you cannot do here. Okay, I can give you a simple example. So here you can take fractional powers.
Yeah.
Let's say if L is degree n, I can consider 1. Here I cannot do it.
Right. Huh. Yeah.
But there are other things like that. Mostly it's fine because so what is the analog of differential operator? Oops. It's V. It's Laurent polynomial S. This is not Euclidean, but it is principal right and left. So the question makes sense. And so basically what I'm saying that all the sufficient statements I have, I can apply for this, but the necessary, for instance, the first theorem is not true. It doesn't.
No questions? Okay, thank you.
Notice